Okay, we're at topic 12, chapter 12, the laws of thermodynamics. Um, and let's go ahead and go to the PowerPoint. And they show a cyclist here. She's basically she's an engine. She's uh, using energy, and we're going to talk about uh, how this energy is used. Um, So let's look here. Work in thermodynamic processes. If you recall, work is equal to force times distance. Here, W is equal to minus F delta Y. Well, the force is equal to the pressure times the area. So work is equal to minus PA delta Y. And the volume, delta V, is equal to A delta Y. So work is equal to minus pressure times delta V. Uh, and just when first semester physics, you learn that work is equal to force times distance. Here again, it's a force on the piston times the distance delta x. Um, so the shaded area represents the work done on the gas. Work is equal to minus P delta V. The area under the curve is P delta V. Area times uh, area equals P times V final minus V initial. That's equal to P delta V. Okay, so the first law of thermodynamics, um, you have the internal energy here of the piston, and you have the this piston pushing on a block. The uh, final energy equals delta V. You see, there's heat is being put into the system that expands the piston. Work is equal to minus P delta V. Work on the environment is equal to minus W. That's P delta V. Um, and it ends up being force times distance, F delta X. Um, okay, so the first law of thermodynamics is that the change in energy is equal to the U final minus U initial equals Q, the energy put into the system plus the work. That is the first law of thermodynamics. Delta U is equal to Q plus work. So we're just repeating uh, the same slide. You can see the Q plus the work here. That's the change in the internal energy. U initial, U final. Delta U equals U final minus U initial equals the Q, the energy put in, plus the work done on the environment. So work, the energy is equal to 3 halves nRT. Delta U equals 3 halves nRT delta T. Now the C, I need to keep up with my notes. CV, that's the oops, the uh, molar specific heat at constant volume. Molar specific heat at constant volume is equal to 3 halves R. That's for monotonic gases. There's 3 degrees of freedom. You know, it can so it's 3 halves R for monotonic gases. For diatomic gases, you add a couple of more degrees of freedom. So the molar specific heat at a constant volume is equal to 5 halves R. And when we come to polyatomic gases, it'll be about 7 halves R. We'll see that in the table in a bit. Um, so delta U equals N CV delta T, where CV is equal to 3 halves R or 5 halves R or 7 halves R for polyatomic gases. And here we have the table. You can see these are monatomic gases. And if you recall, the um, R is equal to 8.31 joules per mole Kelvin. And if you multiply that by 3 halves, you get about 12.5. If you multiply that by 5 halves, you get this, 21 and so. And if you multiply it by 7 halves, you get the average of these values. So we can see that the CV it increases with the increased degrees of freedom. Now CP is for the CP is the molar heat capacity at constant pressure. So we have the molar specific. This is CV is molar specific heat at constant volume. This is the CP is the molar heat capacity at constant pressure. The CP minus CV is about the R. R is equal to 8.31 joules moles degree Kelvin. So, and the gamma, we'll see this later, it's CP divided by CV. And it's about 1.6 something for monatomic, 1.4 for diatomic, and 1.3 for polyatomic gases. So let's keep going. We have different types of processes: isobaric, adiabatic, isovolumetric, and isothermal. Isobaric, think of barometric pressure. Isobaric means at a constant pressure. Adiabatic means that no thermal energy transfer, or that is Q equals 0. So in the delta U equals Q plus work, the change in energy is strictly comes from work. If Q equals 0, isovolumetric, the constant volume means that there is no delta Y, there is no change in the volume. So the work equals 0, so it's all Q. And isothermal, the constant temperature, so that corresponds to delta U equals 0. In other words, there's no change in internal energy of the temperature is constant. Okay, so isobaric processes, the shaded area represents the work done on the gas. Work on the environment is equal to P delta V, so the work is on this system does is minus P delta V. Isobaric processes, delta U equals NCV, delta T, PV equals NRT, Q equals delta U minus work equals delta U plus P delta V. Q equals 3/2 NR delta T plus NR delta T equals 5/2 NRT. That's our CP, the molar heat capacity at constant pressure. Q is equal to NCP delta T. So CP equals CV plus R. We saw from the table that CP minus CV equals R. So here we have, you can see that CP minus, if you take CP minus CV, that equals R. Okay, adiabatic processes, Q equals 0, so delta U equals W. P V gamma is equal to a constant where gamma is equal to CP over CV, where the CP again is the molar heat capacity at constant pressure, and CV is the molar heat, molar specific heat at constant volume. There's the gamma for the different values. Okay, isovolumetric process. If the volume doesn't change, then no work is done. Work is equal to 0. Delta U equals Q is an isovolumetric process. So Q is equal to NCV delta T, where CV is that molar specific heat at a constant volume. Okay, isothermal processes. Isothermal expansion, delta U equals 0 because delta T equals 0. There's no change in temperature, so the internal energy equals 0. So the work is equal to minus Q. So the P equals nRT divided by V. Isothermal process, you can see that work on the environment is equal to nRT natural log of V final divided by V initial. The final volume divided by the initial volume. You can see it, this is an isothermal process. This is an adiabatic process. Adiabatic process is no Q in the system. Okay, the first law of in thermodynamic processes in ideal gases, they give you the remember, delta U equals Q plus W. So this is uh, this is all of those uh, isothermal, uh, delta U equals 0, adiabatic Q equals 0, work uh, is isovolumetric because there's no delta Y in the uh, uh, volume, and you can look at that table and understand it a little bit better. Okay, let's see. Heat engines and the second law of thermodynamics. Cyclic processes. Energy is transferred by heat from a source at a high temperature. Work is done by the engine, and energy is expelled from the engine by heat to a source at lower temperature. Uh, so this is the heat engine. You have a hot reservoir at T hot. You have a cold reservoir at T cold. The engine does work. This is the work of the engine. Energy Q hot enters the engine. Energy QC leaves the engine. So delta U, there's no uh, delta U equals 0. So Q plus W equals 0. So Q net is equal to minus W, which is equals W of the engine. So Q net equals the Q hot minus Q cold. Now the enclosed area equals the net work done. You remember we saw earlier for isobaric, the work under the curve was the work done. So here, the area inside the cycle is the work done. So let me make sure I've got the. Oh, let me find this. Yeah, the E is the efficiency. Um, the work done by the engine for a cyclic process is the area enclosed by the curve representing the process on a PV diagram. The energy efficiency, E of the heat engine, is defined by the work done by the engine divided by the energy absorbed during one cycle. So the uh, the efficiency is 1 minus Q cold, the absolute value of Q cold divided by Q hot. Okay, refrigerators and heat pumps. Work is W is done on the heat pump, so the um, energy Q hot is expelled to the hot reservoir, and energy QC is drawn from the cold reservoir. So in a refrigerator, the coils on the back of the refrigerator energy transfer energy by heat into the air. So this is the hot reservoir. Of course, the inside the refrigerator is the cold reservoir. The coefficient of uh, coefficient of proficient the coefficient of performance, the COP, in the cooling mode is QC divided by the work. Uh, let's see. Uh, yeah, is the cold reservoir divided by the work performed. The coefficient of performance for heating mode is the Q hot divided by the work. Um, the Okay, the second law of thermodynamics, the efficiency is equal to the work, the efficiency, which is equal to the work of the engine divided by Q hot, has to be less than 1. The first law says we can't get a greater amount of energy out of a cyclic process than we put in. And the second law says we can't break even. We can't even break even to 1. It's always going to be less than 1. The second law of thermodynamics. Okay, reversible and irreversible processes. Uh, it's, let's see, let me go back here. Uh, go back to the Kelvin Planck formulation of the second law of thermodynamics. It says that no heat engine operating in the cycle can absorb energy from a reservoir and use it entirely for the performance of an equal amount of work. In other words, it always has to be less than 1. The efficiency of the engine always has to be less than 1. Um, Okay. Um, no matter what engine is used, some energy must be transferred by heat to the cold reservoir. Okay. Uh, Now, reversible and irreversible processes. Now, in truth, most natural processes are known to be reversible. It is possible, if it's moving very slow, uh, to to get close to a reversible process. But most natural processes are known to be reversible. If we were to put small grains of sand and move this very slowly on a frictionless piston, and then remove the sand, it could be that it could be a reversible process. But because of friction and other processes, most processes in nature are not reversible. They're all irreversible. Okay, the Carnot engine. We're going to go through the cycle of A, B, C, and D. You can see A to B, B to C, and C to D. We'll go through those one at a time. From A to B, the gas expands isothermally, gaining energy from the hot reservoir. So you see, you've got the hot reservoir. You're putting energy in. The Q hot. It's going to expand the piston. Now, from B to C, notice that now we don't have a hot reservoir. We've got thermal insulation. The gas expands adiabatically. That means no more energy is being put in. Adiabatically means Q equals 0. Now, from C to D, the gas compresses isothermally, exhausting thermal energy to the cold reservoir. Now, as this is being compressed, it's putting energy into this cold reservoir. Um, and then from D to A, the gas compresses adiabatically. Again, Q equals 0, and there's thermal insulation, so there's no energy being transferred. Q equals 0, and we start the cycle over again. And this is the cycle: A to B, B to C, um, C to D, and then D to A. That the cycles that we just went through are represented here in this PV diagram. Uh, okay. Uh, the efficiency is 1 minus T cold divided by T hot. All Carnot engines operating reversibly between the same two temperatures have the same efficiency. All real engines operate irreversibly due to friction and the brevity of their cycles, and are therefore less efficient than the Carnot engine. Okay, entropy. Delta S equals QR divided by T, where in SI units, it's joules per Kelvin. I need to catch up with my notes. The entropy of the universe increases in all natural processes. So S is the entropy. And let's see. The entropy of the universe increases in all natural processes. I want to make sure I don't. So QR is the energy absorbed or expelled during a reversible constant temperature process between two equilibrium states. Here's another way of looking at it: order and disorder. A disorderly arrangement is much more probable than an orderly one in the laws of nature, if the laws of nature are allowed to act without interference. Um, these are random, these are very ordered. This is very unlikely to get a straight flush. This is very likely to get random cards like this. Okay, so an isolated system tends toward greater disorder. Entropy is a measure of that disorder. The S is equal to KB natural log of W, uh, where the KB is the Boltzmann's constant, and the W is the number proportional to the probability that the system has a particular configuration. So S equals KB natural logarithm of W. Again, where W is a number proportional to the probability that the system has a particular configuration. Here's an example. You can see that you have four marbles, or you have 50, I think it's 50 red marbles and 50 green marbles. Yeah, 50 red and 50 green in a bag. The likelihood that you would draw four in a row is very unlikely. The likelihood that you would get 2 green and 2 red in any of the order, that's the most probable. So this is the W. So S equals KB, natural log of W. Let's see. Oops. No, I'm sorry. My cat's wanting attention here. So the entropy, ice is a very ordered, very ordered system with the because it's cold. There's not a lot of movement, so it's a very ordered system. It's very unlikely that it would transfer energy to the bricks underneath. It's the bricks that are transferring their warmth to the ice and melting the ice. If you were to take a film of it and reverse it, and you would see a pool of water coagulating to form an ice chunk, it would look strange. It wouldn't look natural. In all real processes, the energy available for doing work decreases. So this ball driving towards this wall has a certain amount of energy. Once it hits the wall and rebounds, it has less energy available. Some of that energy has, some of the kinetic energy has been transferred to an increase in internal energy of the ball and the wall. So let's say when you first threw the ball, it could tap a little nail further into the wall. But once it bounces off, it has less of that energy. It wouldn't. Let's say there were a wall on the other side with a nail on it. It wouldn't drive it in as far. It's losing energy as the process continues. Okay, human metabolism, the change in energy over time is equal to the Q divided by time plus work divided by time. And so the metabolic rate is directly proportional to the rate of oxygen consumption by volume. Delta U over delta T is equal to 4.8 times the volume of oxygen divided by time. And here's some rates for a 65 kilogram male. Sleeping, you can see the oxygen used goes from low to high. The metabolic rate goes from low to high. This is in kilocalories per hour. This is in watts. Oops. So these are all about the same. 1 pound of fat is 41,000 kilocalories. Run 1 mile a day for 35 days. That's 4,200 kilocalories. Eat 2 fewer slices of bread per day for 35 days. That's 42 kilocalories. So you can see these comparisons. Physical fitness and the efficiency of the human as a machine. Maximum oxygen consumption rate in milliliters per minute per kilogram. Very poor if it's at 28. Excellent if it's at 70. The body's efficiency is W, the work over delta T divided by the change in internal energy divided by delta T. And here's some metabolic rate for different activities: cycling, pushing loaded coal cars in a mine, shoveling, 505, 525, and 570 increasing. And you can see the watts work divided by time is increasing, and the efficiency is decreasing. Um, okay, and that's it. And then from here we have the topic summary. I'll post that, and we've done all 3 chapters for this opening section.